The next topic is diffraction. This is chapter 5.2.3. By the end of this section, you should be able to understand what is meant by the term diffraction. And also, when I was explaining these previous lessons, I told you about the definitions. And if you scroll down to the last page under the particular subchapter, you will see the definitions. So, for example, let's check this. Yeah, they haven't given that, but they have perhaps given it in the theory part. We will see the details. But if you look at the previous lesson, you can see the definitions are given here and you should know them. Understand what is meant by the term diffraction. Understand the factors that affect the amount of diffraction. Describe an experiment to observe diffraction effects. Okay. What factors affect the amount of diffraction? We will see an experiment to observe diffraction effects. In the O-level class or IGCSE classes also, you would have seen a ripple tank that is used to make waves in water, and with that you would have observed diffraction, interference and other experiments involving the ripple tank, where you can see the behavior of waves, water waves. Okay, let's see. Understand the factors that affect the amount of diffraction. Now, diffraction can happen if most diffraction occurs when the size of the gap or slit is approximately equal to the wavelength of the waves. So for example, over here you can see the green lines are called wave fronts, and between the distance between adjacent wave fronts is a wavelength, and here you can see you get the most diffraction because the size of that gap or slit, it's also called aperture, gap, slit, all mean the same thing. Different past papers may use different words, so it's better if you are familiar with all these different words, not only here, even in other sections of your syllabus. For example, constant, steady, uniform, same, all mean the same thing. So for example, if it's a constant speed, the speed remains throughout the same. So constant speed, uniform speed, steady speed, all mean the same thing. The speed remains the same, in other words. Okay, so you can see, like I said, when the size of the gap is equal to the wavelength of the waves, wavelength is the distance between adjacent wave fronts, then you get most diffraction. Diffraction is the spreading of a wave when it passes through a slit or gap. Let's see the details. Diffraction is a spreading of wave energy through a gap or around an obstacle. Through a gap or around an obstacle. Water waves in a ripple tank diffract obviously when passing through a gap. You can see the waves spread out. Even here it's spreading out. The spreading of the waves when it passes through a gap is called diffraction. Let's see the details. When a wave passes the edge of an obstacle, the wave energy spreads into the space behind the obstacle. So on the other side of the obstacle. So here you can see the waves are coming this way. Imagine this is the sea. This rock is close to the shore. So see, water waves are traveling this way, and then you can see they diffract around the rock. If the obstacle is relatively small, this can mean that the wave energy will pass around both sides of it and continue traveling past the obstacle with no shadow, as if the obstacle were not there, as shown in figure B. Direction of wave travel. Wave energy spreads behind an obstacle. So let's say this is the front and this is the back. If the obstacle is larger, then there may be a shadow region behind it. Say for example, shadow region here, here, here. With no shadow, If the obstacle is relatively small, it can mean that the wave energy will pass around both sides of it and continue traveling past the obstacles with no shadow, as if the obstacle were not there, as shown in figure B. Direction of wave travel. Wave energy spreads behind an obstacle. If the obstacle is larger, then there may be a shadow region behind it, but there will still be diffraction around each edge. If there are two close objects forming a gap, then there will be a diffraction from each edge of the gap, causing the waves to spread out through the gap. You can see that here. See, it's spreading out through each gap, around each gap. Also see figure 5.4.1 for an explanation of why diffraction occurs. 5.4.1 figure. Where is that? Okay, it's I think in the other section. We are right now in 5.2.3, so you can go through that next lesson if you want. Figure 5.4.1 for an explanation of why diffraction occurs. Next column. Water waves in a ripple tank diffract obviously when passed through a gap. You can see that in the diagram, in the photo. Factors affecting diffraction. The amount of diffraction around an obstacle depends on the size comparison between the obstacle and the wavelength of the wave. As the resulting diffraction through a gap is caused by the diffraction at each edge of the gap, there is an optimum. There is an optimum size for the maximum diffraction. Or spreading through a gap. Diffraction happens most when the size of the gap is the same as the wavelength. This is important. In the O-level class or IGCSE classes also you would have learnt it. The amount of diffraction depends on the size of the gap relative to the wavelength. If the gap is too small, very little wave energy can pass through. If the gap is very large, there is little effect, as the majority of the wave passes through undisturbed. Okay, so if the gap is too small, very little wave energy can pass through. If it's very large, so it should be equal to the wavelength of the waves for optimum diffraction. However, when the wavelength matches the gap size, the wave energy is spread very effectively through the gap to fill the space behind, as shown in figure D. This is why we can hear around corners but not see around them. Okay, what does this mean? If you are in one room and somebody is in the living room, your room is maybe next to the living room, for example, and if the door is open, you may be able to hear what people are talking or shouting in the living room. But if somebody points a light, for example, through the door, that light would not get diffracted like the way the sound does. The sound can go around the corners, around like this, it can diffract, but light doesn't diffract through the door because the wavelength of light, visible light, is much smaller. It's 400 to 700 nanometers, so it's much smaller than the width of the doorway. But in the case of sound waves, if you want, even you can calculate the wavelength. In the case of sound waves, the size of the gap is around, or the word we use is matches the gap size. The wavelength of the waves matches the gap size, or the gap size matches the wavelength of the waves. Therefore, you can hear around corners, but you cannot see around them. So I can hear the sound, but I can't see the person behind the wall, because light cannot diffract around the wall, but sound can. It doesn't mean that light cannot diffract. It can diffract, and even in the next lesson you can see diffraction of light. But like I said, the wavelength of light is, visible light is 400 to 700 nanometers. So the width of the gap should be in that range of 400 to 700 nanometers. Then only you can diffract visible light. Very effectively through the gap to fill the space behind, as shown in figure D. This is why we cannot hear around corners, but we can see around them. The typical wavelength for an audible sound ranges from tens of centimeters to a couple of meters. They have given you the wavelength of audible sound. So it can vary from tens of centimeters to a couple of meters. Depending on the exact frequency, they are the same sort of size as potential diffraction obstacles. For example, a doorway might be a meter wide, and a sound of this wavelength would have a frequency of 330 Hz. You can use the equation V equals F lambda, and V is the speed of sound, F is the frequency it's given, and then you can find the wavelength. For example, a doorway might be a meter wide, and a sound of this wavelength would have a frequency of 330, which is a typical speech frequency for humans. So the frequency that we talk is around what is given here, which is a typical speech frequency for humans. This means that a conversation in a room could be heard in the corridor outside the door, as the waves diffract through their original direction through the doorway to be heard out of line of sight. However, with typical visible frequencies of light being of the orders 10 to the power minus 7 meters, these will not diffract perceptibility through the doorway. Okay, so these will not diffract perceptibility through the doorway. Perceptibility. So light from the speakers will only be visible in direct line of sight through the gap, and light travels in straight lines. So it would not possible. So light from the speakers will only be visible in direct light of sign through the gap. Diffraction patterns. The diffraction pattern observed when light passes through a narrow slit, such as in figure E. Okay, so this is about diffraction of light. Yeah, it can be confusing to see the areas where there are no light at all. When the diffraction through a gap suggests that the wave energy spreads out behind the gap, you might expect to see the screen behind the slit illuminated every time. We will look more carefully at interference in the next section. So once they get diffracted, when those wave fronts intersect, we call that interference. Okay, so it doesn't apply only to water waves or sound waves. It can apply even to light waves. The diffraction pattern observed when light passes through a narrow slit, such as in figure E, shows a central maximum and then areas of darkness and further maxima of decreasing intensity. So you can see the brightness decreases to the left and also to the right of this central light. Okay, so we have interference. It not only applies for water waves, even the other types of waves. All the waves, we can say, undergo reflection, refraction and diffraction. We will look more carefully at interference in the next section, but the diffraction patterns we have seen with a laser are examples of an interference pattern. See, considering the waves being diffracted from each end of the slit gives us two waves that will meet at the screen. We do this in dark because then only we can see these specific colors. So green has a certain wavelength, red has another wavelength, and we wouldn't be able to see this pattern clearly if we do it in daylight, because those waves can also interfere or interact with the light from the laser. This would appear as a light spot on the screen at a slightly different place on the screen. These two waves will be completely out of phase and the sum of their displacement will always be 0. So it appears as a dark spot. The diffraction pattern is an example of a standing wave on the screen, where dark spots are nodes and the light spots are antinodes. Okay, I think that's self-explanatory. Alright, so if you look at this last sentence, the diffraction pattern is an example of a standing wave on the screen, where the dark spots are nodes and the light spots are antinodes. So here we have a standing wave and the dark spots are nodes. We saw this in the previous lesson on stationary waves, also called standing waves. If you are not familiar with that, go through the previous lesson, which is the subchapter before this subchapter. Single slit diffraction. If we change the width of the diffraction slit, we will alter the diffraction pattern that we observe. A narrower slit widens the central maximum as well as the further maxima and minima. Okay. Alright, so let's continue this single slit diffraction. If we change the width of the diffraction slit, we alter the diffraction pattern that we observe. A narrower slit widens the central maximum as well as the further maxima and minima. Okay, I already went through that, so you have to remember this. Narrower slit widens the central maximum as well as the further maxima and minima. Diffraction patterns of light observed on a screen shows a bright white central maximum, that is this, also we can say this, surrounded by areas of darkness. You see between the dots there is a gap which is dark, it's darkness, and further bright spots that have decreasing brightness from the center. So from the center, when you go to the right or to the left, the brightness decreases. Okay, then we have diffraction grating. Alright, diffraction grating. A diffraction grating is a device that will cause multiple diffraction patterns which then overlap. So multiple diffraction patterns that overlap, creating an interference pattern with a mathematically well-defined spacing between bright and dark spots. It is a collection of a very large number of slits through which the waves can pass. These slits are parallel and have a fixed distance between each slit. Diffraction grating can be used to examine line spectra. The pattern produced by each color passing through a diffraction grating shows the equation. You should know this equation: n lambda equals d sine theta, where theta is the angle between the original direction of the waves and the direction of a bright spot. Lambda is the wavelength of the light used. B is the spacing between the slits, that is also called grating spacing, slits on the grating, and N is called the order. The order is the bright spot number from the central maximum, N equals 0. So we can see all these details. I think I have also discussed a past paper question where I show this picture, and I have added to the picture, I have written all the equations. You all can also watch that video. I think it's in one of the past Edexcel IAS papers where you had this question on diffraction grating. And you can see here the angle is labeled: the central bright spot, diffraction grating, laser. This is the angle. Where theta is the angle between the original direction of waves and direction of bright spot. So here this is the angle from here to the bright spot, central maximum, the one that is most, or the brightest in other words. This, so we measure the angle like this, from here to here, from here to there. Okay, so that's what's explained here. The order is the bright spot number from the central maximum. So here we have in the middle N equals 0. N equals 0 is the central bright spot. So therefore this will be N equals 1, this will be N equals 2, this will be N equals 3. It's already given here. Now if they give you the distance between the gratings, okay, then you can find the number of lines in that grating. Grating spacing is often quoted as number of lines per millimeter or per millimeter, per meter or per millimeter, which means that to find D you will need to do an initial calculation in which D is equal to 1 divided by number per meter. Okay, so 1 by the way, this is if it's in SI units, meters. Here if it's in millimeters, you know you have 1000 millimeters in 1 meter. So 1 meter is 10 to the power minus 3 millimeters. Okay, to help us understand this better, let's go through this diagram. Investigating diffraction with a laser. You can use a laser pointer or laboratory experiment laser to demonstrate diffraction. A diffraction grating investigation allows careful study of the light making up the spectrum from any light source. Astronomers use this to study the spectra from stars. So here we have the diffraction grating, then this is the angle. If you substitute 1 for n, the first one is 1, second one is 2. So if you substitute that number here, then the angle will be the angle from the central maximum to that first order, second order, third order maxima. Okay, so that's the angle. Then D already, it depends on the diffraction grating only. Diffraction grating will produce a series of bright spots at decreasing angles from the center. Decreasing angles from the center. Okay. A diffraction grating will produce a series of bright spots at increasing angles from the center. Diffraction gratings are manufactured to have a fixed spacing d between lines on the grating, and this will be printed on the grating. By measuring the angle to each maximum brightness spot created by a diffraction grating, you can calculate the wavelength of the light used from the diffraction grating equation. Okay, so I think you understand that. CDs have a series of very close lines marked on them and act as a diffraction grating that reflects. This causes the spectrum of colors that can be seen on them from white light that hits the surface. Again, I think this is self-explanatory. So let's go to the next part and then we will write the note. Yeah, so that's the end of that on diffraction. But first we'll go through the important points here. So this diagram is very important. You should be able to label n equals 1, 2, 3. Then lambda, what is lambda? You should know. Theta is the angle between n equals 0 and n equals 1, n equals 2 or n equals 3. So n is the first order, second order, third order, it can go on. Okay, yeah, so that's the end of that regarding this. And then you should know all the terms here: n lambda, d sine theta. And you should know what is diffraction. Yeah, so let's see. Understand what is meant by the term diffraction. Understand the factors that affect the amount of diffraction. We went through all this. Describe an experiment to observe diffraction effects. There are several. So you can use this. The Young's double slit experiment is when you have a double slit. So don't confuse that with this. I can show you both. Actually, we have another book for Cambridge students. So here is the equation, but that is when you have a double slit. Okay, here you have a diffraction grating. So the equation you have to apply whenever you see diffraction grating is this equation. Alright, so that's the end of that lesson on diffraction. And in the next video we will see the next topic, 5.2.4 I think. Wave interference, yes.